Hello, everyone. I am Samuel Adel. I am a senior petroleum engineer with 13 years of experience in hydraulic fracturing. I actually conducted thousands of hydraulic fracturing treatments, acid fracturing, acid treatments, and we only have 30 minutes to cover the hydraulic fracturing treatments. So we will go really quick as an overview for hydraulic fracturing. And we will have 10 minutes at the end of this webinar for any question. So let's start. Okay, guys, what is the motivation for frac engineering and diagnostic? Actually, hydraulic fracturing is done for well stimulation, not for proppant disposal. I mean, it's too easy to just finish the proppant placement in any reservoir. That's too easy. I mean, if you have just 100,000 pounds of proppant or 200,000 pounds of proppants, it's too easy to finish the placement. But is this a successful job? You need to think about this. What is the target from a hydraulic fracturing job? The target from any hydraulic fracturing job is actually to achieve a certain fold of increase and a stable production. What I mean by a stable production. Stable production means that you achieve the cume of oil or gas that you want. So if you just finished proppant placement and didn't achieve your target fold of increase and cume of oil or gas, you cannot consider this as a successful hydraulic fracturing job. So you have to keep the goal behind the hydraulic fracturing during the design phase. So let's talk about the frac models. We already have many hydraulic fracture models available. We have the classic 2D models, BKN and KHD, and as you know, this is very simple models. And we have pseudo 3D models, and we have a parametric and cell-based models. And the most advanced one is the planar 3D models. And as you can see in this table, okay, let me turn this mouse. Okay, here. Yeah, here you are. So as you can see here from this table, we already have many different commercial softwares from different companies. The simple one actually here is the classic 2D models. And we have here pseudo 3D parametric models. FracPro is actually very famous in this category. And we have in a pseudo 3D cell based, and we have STEMplan and FracKit. This is the most famous one in this category. And the last one actually is the planar 3D model. And the most famous one is actually Goofer. So to keep it simple, as it goes down, the accuracy of the results will be much, much higher. But at the same time, the requirements to run this software simulation will be much, much higher as well. So the question is, which one we should use? It's actually based on the available time and the available data. I mean, if you have everything, I mean, if you have a well survey, you have a complete reservoir properties and geomechanics profile, Young-Morris boson ratio, stress profile, and you already have a local experience and you have a mechanical earth model and everything is ready. So you have to use the planar 3D, like Goofer, for example. And this will give you the best results you can get from a frac model. But if you don't have even logs, if you don't have even triple combo, you cannot even run pseudo 3D model. So that's why you can use just a 2D classic model. So what about time? If you just need a quick results, you just have 1 hour and you need a quick results just to figure everything out, you have to go with classic 2D model. But if you have like a campaign, okay, we will go with a huge project and we will go for like 1,000 hydraulic fracturing. As I said, we already have many hydraulic fracturing models, and you need to make a decision which one you should use based on the available data and the available time for you, and actually based on the available hardware. Because in Goofer Actually, if you have a really complicated mechanical earth model with reservoir properties and geomechanical properties, this model actually can run maybe more than 20 hours, and you need like a mainframe to do this run. So it's all about the ability of this hydraulic fracture model to predict the results after hydraulic fracture model. So if your model cannot predict the fault increase that will happen after the hydraulic fracturing job, and it cannot predict the post-frac production profile, I mean the cum oil and gas. So why you need this model, right? I mean, you need to get a model to get the accurate prediction of the results. So let's move to the decision. So, okay, if you have a carbonate formation and you need a stimulation treatment, so which technique will be the optimum one for your reservoir? Prop frac, acid frac, or just an acid treatment? So this decision tree is really like a rule of thumb. This is a very simple tree, and it's based on many factors like solubility, heterogeneity of the reservoir, closure stress, permeability value. And based on these factors, you can determine which stimulation technique you will proceed with. And this guy is very critical, because if you already decided to go with just an acid frac and you figured out that this is not was the optimum choice for this reservoir, I mean, the cost will be extremely high. I'm talking here about thousands of treatments in large companies. So you really need to collect these data and make a decision based on it. So what is best candidates for any hydraulic fracturing treatment? We have excellent candidates like damages and low permeability reservoirs with sufficient oil and gas. This is the excellent candidates for any prop frac jobs. But if you have a poor candidates like reservoir with limited reserves, this is not a good candidate for a hydraulic fracking. Why? Because even if you proceeded with a hydraulic frac for a limited resource, this will not increase the oil in place. And the whole cum of oil will finish within a very limited period of time. So the hydraulic fracturing in this case is not the optimum solution. If you have a thin reservoir with poor barriers, the height of the frac will penetrate these barriers and propagate to maybe a gas cap or a water zone, and the results will not be good in this case. And even if you have a low pressure reservoir, the clean-out process will be extremely difficult in this case. Even if you use things like foam frac or energized fraction fluid, this will be difficult for any frac engineer. And maybe fraction will not be the optimum choice for this one. And the reservoirs where stimulation can penetrate water zones, you have to avoid all these candidates by any cost. Why? Because if the hydraulic fracturing penetrate a water zone, the water cut percent will be extremely high. And believe me, based on my practical experience, if your hydraulic fracturing penetrate to a water zone, it will be really hard to control the water production in this case. So what about the hydraulic fracturing equipments? Hydraulic fracturing equipments, actually, as you can see, there is unconventional reservoirs and there is a conventional reservoirs. Unconventional reservoirs, the layout will be a little bit complicated because we may have many hydraulic fracturing pumps, a lot of water tanks, and maybe the whole layout, maybe like, as you can see in this figure, this is a huge layout, okay? If you compare this layout to the conventional one, as you can see here, we just have like 5 or 6 water tanks. We here have a huge water tanks. I mean, this is maybe like a 20 frac tanks, the volume of it. And as you can see, we have here like more than 40 or even 50 frac pumps. We have here like just 5 or 3. So from the operational wise, from operation side, there is a huge difference between the unconventional and conventional hydraulic fracturing. And what is the component? This is the main component of a hydraulic frac equipment: water tanks, wireline crew, frac pumps, chemicals, sand or proppant, blender, warehouse, and data file. And recently, we have something called Express Sand Delivery System. This system is actually a famous system in US. They don't use actually sandbags or sandcastle anymore. They use this system, Express Sand. And as you can see, sand actually come as cubes. And they are doing this. These cubes actually make the downtime and extremely low. And the operation will be really fast because they are pumping, not like us here in Egypt. Here in Egypt, we have a convention. Most 90% of our reservoirs actually are conventional reservoirs, and we pump from 100,000 pounds of proppant per well to like 2,000 pound proppant. So this is very small volume if you compare it with the unconventional treatment in US. In US, they pumping millions of sand in a single well. So that's why they are using these sand cubes. So let us talk about the closure equation. This is the closure pressure or the minimum horizontal stress. And as you can see, it seems like a little bit complicated equation, but you really need to understand something. This actual in-situ stress or the minimum horizontal stress can only be determined by direct measurement. Why is that? Because we have here two terms. These two terms, tectonic forces and strain. These two terms actually deal with the tectonic forces. And there is no test, there is no poor test or anything you can do to actually in lab to measure these two terms. You have to go with actual measurement. You have to go with a DFAT or mini frac analysis. And this is here handling of tectonic stress. There are two ways actually to handle tectonic stress. The first one, you can use a value of a tectonic stress, like, okay, we have like 500 psi, and add this value to the whole stress profile, and this will shift the whole stress profile 500 psi. But this is not accurate. Why? Because as you know, the Young modulus of the shale is completely different than the Young's modulus of the sandstone. And if you add the same 500 psi to the shale and sandstone, this means that both of them react on the same way to the stress, and this is completely wrong. And that's why we actually prefer to use the strain as a value to calibrate your estimated stress. So let me give you an example. If the estimated calculation of this stress actually was like 3,500, and you go with the DFAT analysis and you find out that the actual stress is 4,500. So how to calibrate this actual stress? You have to add like 200 micron strain, for example, and you will see this will shift the whole stress profile to 4,500. If you get this 4,500, so everything will be okay. If you didn't reach to 4,500, in this case, you have to add tectonic stress to the whole profile. This is the most accurate way to calibrate this profile. And if you don't do this, believe me, frac geometry will be completely wrong, and the results, the post-frac production profile will be completely wrong. So you really need to understand the effect of the microstrain and the tectonic forces on the minimum horizontal stress or closure stress. Otherwise, the results will be really off. So we have two types of Young's modulus. The first one is a static modulus. This is a large amplitude at zero frequency, and you can do this by load frame tests in lab. And the other one is the dynamic modulus. This is a small amplitude at high frequency. This is coming from the Quest waves. Which one we use in the hydraulic fracturing design? The static one. which one we get from the logs is the dynamic one. So how can we convert the dynamic to static modulus? You have to get something like this. This is actually a correlation. And as you can see, on the x-axis, we have the static Young's modulus. On the y-axis, we have the dynamic Young's modulus. And this correlation, you can convert the dynamic Young's modulus coming from logs to the static Young's modulus to build your Fractal model. What if you don't have this correlation? You have to build it. You have to build your local correlation based on your core and based on your lab test, actual lab test. And this is very crucial to calibrate any Fractal models. So logging, we are familiar with the triple combo and the sonic logs. We have density log, gamma ray, resistivity, acoustic. We have all these logs measure many different parameters, but you have to keep in mind, none of these measure pressure or stress. None actually measure rock, elastic, or mechanical properties. You have to keep this in mind. How to measure stress? You have to go with the DFAT and the millifrac. There is no can actually get stresses. All these logs can get just an estimation. From dipole sonic log, you can get just an estimation, not a real measurement. And you cannot get pore pressure from logs. You have to go with the downhole memory gauge, build up RFT, DT, anything. You have to measure the pore pressure. Pore pressure and the stress, minimum horizontal stress, are actually the most important parameters in reservoir characteristics if you need an accurate reaction log. So we talked a lot about the DFAT. The DFAT. DFAT is a diagnostic fracture injectivity. And this is a unique test. This is a test conducted before a main frac job. And this DFAT is not a microfrac, it's not a mini frac, it's not a data frac, it is not a pressure rebound test, it is not reservoir limits test. I know that we already have a mini reservoir guys, and they already tell you, okay, this is like a build-up test, it's like a drawdown test, it's just a well testing. Believe me, it's not. It's a completely different story. And the workflow of the DFAT analysis is a completely different story. And Nolte said, if you don't do this and do it right, don't even think of using a numerical simulator for frac design. If you don't do a DFAT analysis right, don't use any numerical simulation, because as you know, rubbish in, rubbish out. If you don't have an accurate model, the results will be completely wrong. So if you don't know how to do a DFAT and analyze it in an appropriate way, forget about frac simulation, because you will get nothing from a simulation. So what is the events observed during a DFAT procedure? First of all, you will observe something like this. This is a breakdown pressure. This is a sudden drop in pressure. This means that you already break the formation. If you didn't get this and you get something like this, this is a smooth curve of pressure buildup. This means that you already break down this formation before, maybe during the drilling, and you just reopen the frac again. Okay. Then you will go with the step down test and ISIB. This is ISIB. This is instantaneous shutting pressure. Then this is the leak off. After shutting the pumps, you will get pressure drop until you hit the closure pressure. The difference between the ISIB and the closure pressure is actually a net pressure, and we call it process zone stress. Okay, then the leak off will continue until you reach to pseudo-linear behavior, then pseudo-radial behavior. Okay, from this period, actually you can get the net pressure, ISIB gradient, closure gradient. You can get the leak off behavior. You can get the RP, leak off coefficient. All these parameters called before closure analysis. Okay. And after this point, pseudo-linear and pseudo-radial, we call it after closure analysis. Pseudo-linear, we can get the pore pressure from pseudo-linear, and pseudo-radial, we can get the reservoir permeability. So that's why this defect analysis is extremely important, and you cannot proceed with the hydraulic frac job without a defect analysis. I actually heard many guys actually from operation, they will tell you, okay, let's speed up the operation and let's cancel the defect analysis. We don't need that. We have all the information and we can go ahead. Believe me, this will be a blind hydraulic fracturing job, because the stress, Young's Poisson ratio, reservoir characteristics, this may change from a well to another well, even if they are very close together, because we already have a huge heterogeneity in our reservoirs. And even if you have a fault, you have to predict that the whole characteristics will be completely different story. So this defect will consume just 5 minutes. You need to pump for just 5 minutes. So please, guys, don't cancel defect just to make it fast, because the information coming from this defect is really crucial for any frac model. So this is some constraints of a defect. You have to reach to 10 barrel per minute. This is to guarantee that you already exceeded the breakdown pressure and to make a stable frac. And this equation will illustrate the relationship between the T closure, okay? As you can see here, time to reach closure is approximately pumping time over 3 estimate permeability, okay? This is very important for any frac engineer, because this is like a QA, QC for the defect analysis. If you already know the permeability and the pumping time, you have to guess when you should see the closure. It's very critical for any frac engineer, if you already there in the van, to know when we should expect the closure. And this one will tell you when you should see the start of the pseudolinear. T pseudolinear equal 3 T closure. And another big deal, actually, how to pick an ISIB with high torque capacity. If you don't have any torque capacity, this will be extremely simple for anyone. You will have water hammerings, you will have a very good communication between the well bore and the frac body, and it's too easy to pick the ISIB. But what if you have a high torque capacity? This is a little bit complicated issue, and the best way to get the ISIB is by do a well bore blowdown analysis. This well bore blowdown analysis coming from Beaupre, from Gopher, and this is an advanced technique. And believe me, this is the most accurate technique to get the ISIB. And you need to know this technique, guys, because I already heard many people coming from different backgrounds, and they actually do many techniques, and it's all of them are wrong, really wrong. But if you go behind the theoretical background behind this well bore blowdown, you will find that this is one of the most accurate methods to get the ISIB. So why it's important to get the ISIB? Because if you pick the ISIB wrong, the net pressure will be wrong. And if the net pressure wrong, the frac geometry will be wrong, and the post-frac production profile will be wrong. So it's really important to get the right ISIB. And we can talk about this method more during the upcoming course for sure. So this is a typical derivative shape in G function. This is the bottom hole pressure, and this is the G function, and this is the first derivative. The deviation from the straight line, this is the closure, this is the normal leak off, this is the enhanced or accelerated leak off, and this is delayed, we call it variable storage leak off. And you need to know each one of these and how to deal with each one of these during the frac design. Because if you already have a PDL leak off design with an RP exceeding 1.3, you have to be careful, because this means that the leak off will be extremely high and the screen out possibility is really high. So you have to adjust your frac design based on this RB and this hump. And the same thing here in the belly, and we call it variable storage. If you have a variable storage, You have to be careful, guys. You have to suspend the whole operation and design a completely different technique if you have a huge building, because this screen out probability, I mean, if the RP is less than 0.8 or 0.7, the possibility of a screen out may exceed 90%. And in certain cases, you have to cancel the whole frag job based on this leak off. That's why DFAT is extremely important, guys, and how to detect the leak off behavior closure pressure. So let's talk about the permeability, reservoir permeability. Reservoir permeability, guys, is extremely important for any hydraulic fracturing job. Why? Because if you have a tight reservoir, the goal from the hydraulic fracturing job is to create a long frac. If the reservoir permeability is high, the goal from a hydraulic fracturing job is to create a high conductivity. So if you don't know the permeability of the reservoir, how can you design a hydraulic fracturing job? Actually, you can't, right? So that's why you cannot proceed with a hydraulic fracturing job without knowing the permeability value. That's it. And reservoir guys will tell you, okay, we cannot get the permeability. If you cannot get the permeability from a DFAT because if you have a high permeability or you have a depleted reservoir, you can use this equation. This equation coming from Gopher, from Poppery, and this is an empirical correlation. And you can use this correlation to get an estimation of permeability. This will be better than nothing, guys. And believe me, I use this correlation for a very long period of time. And the percent of error actually not exceeding 15%. And this is very good. If you have nothing, you have to use these correlations. So, okay. People think the hydraulic fracturing actually propagate through the perforation tunnel. And believe me, this is completely wrong. Hydraulic fracturing doesn't propagate through a perforation tunnel. And this is the proof. This is an actual job. And this is an actual perforation tunnel. This is the casing, and this is a cement sheet. And as you can see here, we have the perforation, and this is the tip of the perforation. And this liquid, this blue, dark blue liquid, this is actually a hydraulic fluid, hydraulic fracturing fluid. As you can see, hydraulic fracturing coming from here, from casing, passing through the cement, and it doesn't propagate through the tunnel of the perf. It propagates through the space between the cement and the formation. Why is this? As you can see here in the blue picture, this is the tunnel of the perforation. And we have here a deformation. This is a plastic deformation of the formation. And that's why frac fluid cannot penetrate this area, cannot go through the perforation tunnel, because this deformation actually creating a huge stress, near wear pore stress. So the frac fluid will go through the least resistance. So it will go through the cement and the formation, and it will avoid the perforation. This is very important to understand. Why? Because what do you need from the perforation? If you know that you will proceed with a hydraulic fracturing job, no one actually care about the perforation length. We really care about the entrance hole diameter only, because the function of the perforation before a hydraulic fracturing job is just to pass the cement sheet and casing, and that's it, guys. So you really have to care about the entrance hole diameter only. So what about proband selection? Proband selection, you have to consider many factors: the embedment, the crushing, the conductivity, size, and concentration. Why proband is extremely important? Because this proband is the main reason behind the frac conductivity. So if you didn't consider the dynamic conductivity and the static conductivity, your results and your prediction model will be completely wrong. So you have to consider all of these factors. For sure, this is a long story, and we will discuss all of these factors during the upcoming course. Frac fluids. We have many frac fluids. Really, we have more than 20 frac fluids. but these are the main one. Conventional frac, this is water-based, cross-linked fluids, and we have here foam fluids, nitrogen or carbon dioxide, and we use them mainly in the low pressure wells. And we have oil-based frac fluids. We use them with the water-sensitive formations, and we have slick water linear gel. This is the low viscosity frac fluid. We usually mainly with the unconventional reservoirs. How to select the frac fluids and how to select the chemicals, additives. I mean, we have more than 1,000 chemical additives actually available in the market. How to choose each one, or how to choose the frac fluids. We will discuss this in detail for sure in the upcoming course. So this is actually the last stage of any hydraulic fracturing job. If you conducted the hydraulic fracturing job and you put the well on production, frac engineer will tell you, okay, I'm done. This is my job, and that's it. Believe me, this is not the whole job. We must know what was achieved to improve the design, or the design effort was wasted. Why? Because you need to get a match between your predicted post-frac production profile and the actual one. How to get this match? You need to understand the actual frac conductivity. So what is the fracture conductivity? Fracture conductivity depends on two parameters, width and back permeability. Width determined by the proppant concentration, closure stress, filter kick, and imbimbment, and back permeability determined by the proppant size, strength, packing and porosity, regain permeability, and gel cleanup, non-darse flow, and multi-phase flow. So if you didn't succeed to get an optimum match between the actual post-frac production profile and the estimated one or the calculated one, so why you are running a frac simulator? The whole purpose from any frac model is to predict what will happen after the hydraulic fracture model, to predict the fold of increase and the cum of oil. Because if you have the same well and the same formation, and you pumped like 100,000 pounds of proppant, you will get fold of increase 2, for example. What if you pumped 200,000 pounds of proppant? You will get fold of increase 2 as well. So you will tell me, okay, Samuel, we already pumped 200,000 and 100,000 and we get the same result. I will tell you no. Look at the long run. Look at the cum of oil and gas. 2,000 pounds of proppant will give you a longer production, a higher cum of oil and gas. And that's why it's really important to get a good post-job analysis. If you have a conventional reservoir, this post-job analysis may conduct maybe within 1 year from a hydraulic fracturing job, from the main job. If you have unconventional reservoir, this reservoir actually can produce for more than 20 years, 25 years. So it's really important to match and rematch your post-frac production profile every 3 months to make sure that you understand the actual frac conductivity and the actual frac length already created. And if you get something mismatch, you have to understand what's going on here. And this is what we call a learning curve. If you have like 1,000 hydraulic fracturing job, it will not be like 2 hydraulic fracturing job. After 1,000 hydraulic fracturing job, you should get a good match between the model results and the actual results. And this is the ultimate goal from any frac model, to predict what will happen after a hydraulic fracture. And as you can see here, we have many parameters. We have parameters affect on the frac treatment. We have parameter effect on the fraction, defect, and production profile. And you have to understand each parameter of this one. and its impact on the net pressure, process zone stress, surface pressure, and the production profile. And believe me, if you don't understand each one of these parameters and how it impact on the frac treatments, your prediction will be not accurate. And if your prediction not accurate, why you are running a frac simulator, why you are doing a design, why you are collecting the data. So you have to do both job analysis well to get a good results. Okay, guys, we just finished. And any questions? Hello?
Hello.
Yes.
Yes. Hi, Samuel. Very nice presentation, I would say, and very informative. I am Gautam Tibrewal. I am working as a frac specialist here in India with ONGC. So we are performing frac jobs day in and day out in sandstone reservoirs. But the thing is that one problem which we are facing is that what FCD are you targeting for frac jobs? Because during the design, when you do the iterations, so what is the optimum FCD which you are targeting uh, to determine the optimum job size?
Yes. Actually, the sound is not clear, but as I understand, you are asking about the optimum FCD or fold increase for the sandstone, right?
Yes.
Yes. Okay, guys. We have many models for the optimization of the FCD and the fold increase. Fold increase, guys, may range from 1.1 to 10 fold increase. And believe me, based on my experience, you can design a hydraulic fracturing to hit 10-fold increase each time. This is easy. This is based on your software. This is a theoretical model, but in real life, this is a completely different story. So the answer for your question is what is the economics behind this hydraulic fracturing job?